let's do one in 3 dimensions. If you think about this vector field, if you ignore the z component, then it's just this spin field again. And so if we ignored the z, then at every location, no matter what z is, we have these vectors that are spinning around, right? Now if we look at the z coordinate of our spin field, it's always moving us up 1. So if we look at this sort of in 3 dimensions, x, y, and z, at every location, no matter where we are, we have a vector that's sort of spinning around the z-axis and moving up slightly. So this is our vector field is sort of like a spinning tornado that's carrying things upward at the same time. No matter where we go, we have this vector field that's spinning around. It's a little bit hard to see, but we could use Maple to do it. If we have a 3-dimensional vector field, then the command in Maple is field plot 3D. So we give our vector field, which was minus y, x, and 1, and then we just put ranges on our variables. We can do from -2 to 2, and from -2 to 2, and z from -2 to 2. So we'll just look at this vector field in this little box here. And we look at it, and we've got, yep. If you notice, if you look down on it, right, it's always spinning around that z-axis. And then if you look at it from the side, the vectors are always climbing by a unit length of 1. There's one last vector field that's important that we can analyze here. Suppose you want to find a vector field in 3 dimensions that always points to the origin, and you want to make the magnitude inversely proportional to the square of the distance from the origin. This is important for forces like gravity, because basically, like the gravity around the Earth, the further you move away from the Earth, the gravity that Earth creates gets spread over a larger and larger surface area, basically the surface area of a sphere, and so its strength decreases. The surface area of a sphere is proportional to r squared, so it gets spread over or divided by the distance, the radius of that sphere. So that's actually the gravitational law that says that the force between 2 objects is equal to big G, the mass of the first object, the mass of the second object, divided by the distance between the objects squared. So this is an inverse square law, so it changes inversely it's inversely proportional to the square of the distance between the 2 objects. So let's see, we've got to do 2 things. We've got to create a vector field. Let's create a vector field, I'll call it bold G, x, y, and z, that points to the origin. Now we saw in 2 dimensions that if you did this vector x, y, you got that radial field, right? If you do x, y, z, then whatever your location is, you have a vector that continues on in the direction that would go from the origin to your location. So this is a vector field that goes out from a point, goes away from the origin. So if we want to go towards the origin, we should do that. We should change the direction by multiplying through by a -1. Now, if we want to give it a particular magnitude, the first thing we got to do is to take this vector field and divide it by its length. So that will make a vector field whose length is always 1. So, of course, the length of this vector field is the square root of the sum of the squares. So the length of this vector, the magnitude of this vector, is the square root of x squared plus y squared plus z squared. This is now a vector field, but all the vectors have length 1. We want them to have length that's proportional to the square of the distance from the origin. So our final vector field is going to be to take our unit vector field. So all the vectors here have length 1. We divide by the length of G, right? And then also divide by the distance from the origin. The distance from the origin squared, which is going to be x squared plus y squared plus z squared. You see what we get is we get a vector field looks like this. negative x, negative y, and negative z. That just makes it so that we point towards the origin, and then we're just rescaling it. This is the square root of x squared plus y squared plus z squared, and then we have x squared plus y squared plus z squared to the 1. So all together we have x squared plus y squared plus z squared to the 3/2. So if you look at the length of this vector, the length of f, then you're always going to get 1, the length of this is always going to be 1 over x squared plus y squared plus z squared, which is the square of the distance from the origin. So this is the kind of vector field that you see around the Earth, or that the vector field that you see around the Sun. Let's just plot it really quick in Maple just so that we can look at it. Again, we can use the command field plot 3D. So our vector field is, let's see, we had negative x over x squared plus y squared plus z squared to the 3/2 power, and then all the other terms were basically the same. So the only change is that instead of a negative x we have a negative y, or for the z one we have a negative z. Then we can give a range here about x equals negative 2 to 2, y equals negative 2 to 2, and z equals negative 2 to 2. You can see our vector field is always pointing right in the inward. The closer we get to the origin, the stronger the vector field is, right? That's because our distance to the origin gets smaller, and we have a less strong field. Now the colors are kind of hard to see on this. Maybe I'll just change this color to black so that we don't have the color problem. That makes it a little bit easier to see our vector field. Could also use this thickness attribute. If I set thickness equal 3, that makes the vectors a little bit thicker so that I can see them. So that's how we plot vector fields using Maple. If it's 2D, field plot. If it's 3D, field plot 3D.